Okay, so this is problem 5.3 from the text, and it shows a 3D problem that we're going to approximate as a 2D problem. So here's the problem. It's a rear door of a minivan. You can see it's got a hinge here at point A, and it's got two struts that stretch between points B and C. You can only see one, but there's another one just in back of it. The door weighs 350 newtons, and the center of mass is point D here. And we want to be able to close the door by putting a 40 Newton vertical force here at point E. And so the question asks, if this is the case, then what are the forces that the struts have to provide, and then what are the reaction force at the hinge? So go ahead and take a crack at that problem, and then come back and we'll go through it together. Alright, so the problem is a pretty simple application of the equilibrium equations in 2 dimensions, right? So we need to require that the sum of all the forces on the door is equal to 0, and that the sum of the moments are 0. And so in 2 dimensions, the sum of forces is actually 2 equations, one for x, one for y. And the sum of moments is just going to be 1 equation, right? Because the moments will all be in the z direction. So if you look at the problem, you can see that we know the direction of the strut force, so one unknown is going to be the magnitude, and we don't know the direction or the magnitude of the reaction force at A, so we'll have 2 unknowns there. And so that's 3 unknowns in those 3 equations, and we should be good. So let's go ahead and try to derive these equations. So we have completely specified the geometry. We have points A, B, C, D, and E. And then we got to think about the forces. So there's a force applied here at point E, which is from the hand, and it's 40 newtons and down. So that's specified. There's a force applied here at point D, which is the weight of the door, and that's 350 newtons and down. So that's also specified. Now we know the direction associated with the force from the struts, and that's given by the position vector RCB. And we can calculate that position vector. And so then the force that's applied at location B is going to be twice the force of a strut, the magnitude of the force of a strut, in the direction defined by this unit vector, which is related to the position vector RCB. So there's an unknown there. And then finally we'll impose that the sum of all these forces must be equal to 0. So the sum of the forces include force A, force B, force D, and force E, and that has to equal not scalar 0, but the 2D vector 0. So that's 2 equations in our 3 unknowns, and then the last equation is that the moment about any point, so in this case we'll take the moment about point A, has to be 0. So the moment about point A includes a moment related to the force B, so that's RAB cross FB, a moment related to the force D, RAD cross FD, and then finally a moment related to the force E, RAE cross FE. And so that's our last equation. And at this point we should have enough equations and enough unknowns that we can solve. So we'll go ahead and enter these equations into ease. So the first thing we're going to do is enter all of these coordinates. So these are all 2D vectors because they all have 2 components. So A, B, C, D, and E are all defined as a 2D vector, and we'll just use the vector assign command to do that. And we have to define an origin, which we will define as being sort of the lowest and leftmost point on this plot. So yeah, we'll take a little bit to assign all of these coordinates, and then once that's done, we also need to assign the force from the hand, which is 40 newtons, and the force related to the weight of the door, which is 350 newtons. And then we're going to define 4 forces as 2D vectors, and these are the 4 forces in the problem, F, A, B, D, and E. And we'll also want the position vector RCB to be a vector, a 2D vector. So FE is minus F hand times the unit vector in the y direction, so unit vector J, FD is minus W times the unit vector J. RCB is just B minus C, and then FB is twice the strut force times RCB divided by its magnitude, so the unit vector in that direction. And then we have the sum of these forces has to equal 0. And then finally, we will put an equation related to the moment. So in order to do that, I need vectors corresponding to RAB, RAD, and RAE. And RAB is just B minus A, RAD is D minus A, RAE is E minus A. And then the moments about point A are the cross product of these vectors. So we have vector cross of RAB FB plus vector cross of RAD FD plus vector cross of RAE FE. And because we're using 2D vectors, this is just equal to 0, the scalar 0. So at this point, we have enough unknowns and enough equations. We should probably go through and set all of our units, but if we go ahead and solve, you can see that the strut force is 789.2 newtons, and the reaction on force on the hinge is a force that has 1239 newtons in the x direction and minus 588 newtons in the y direction, and that all agrees with the solution from the text. So we're going to go ahead and visualize these results using a 2D vector plot. So the easiest way to do this is with the $vector plot 2D directive, which is available in the professional version of these. Otherwise, you'll need to go and make a vector plot one vector at a time. But here I'll use the $vector plot 2D. I'll name the plot vector plot, and I'm going to put in each of these forces, and I'm going to locate the force at the position where it's applied. So FA is going to be located at location A, and we'll make it red. FB located at B, make it red. FD located at D, also red, and FE located at E, also red. And if I solve now, I get this vector plot shown here. And one thing you can see is that the strut force and the reaction at the hinge are the two biggest forces, and the force in the hand is actually quite small, right? So these forces are almost in equilibrium with the weight, and then the person is just applying a very small force to pull the force down, to pull the door down. And finally, let's go ahead and look at some aspect of the design to see how it actually affects the performance of the door. And you can do this all different ways. This is the great thing about having the model programmed in a computer program, is you can carry out these kind of parametric studies. So what I'm going to do is assume that the strut provides a constant force, and I'm going to vary the position of this coordinate B where the strut is mounted, and see how that affects the force required by the hand. And you could think of an infinite number of these kinds of studies. But let's go ahead and if you're using a professional version of these, I'm going to go ahead and do this in a different tab. So I'll define a new tab. I'll copy all of my equations into that tab. And now what I'm going to do is set the strut force to 789.2 newtons, which is what I just calculated, and comment out the force from the hand. So now it's figuring out the force from the hand given that strut force. And of course, if I solve now, I should get exactly 40 newtons, because that's the solution. But I can now comment out the coordinate B, which gives me two unknowns, bx and by, and see how the coordinate b affects the force from the hand. And so we'll make a parametric table. I have 100 rows. Include the variables bx, by, and f hand. And I'm just going to vary bx from 400 to 700 millimeters, and by from 300 to 600 millimeters. So I'm just moving that coordinate around in a little box here. And I'll do that in a way that gives me a nice grid of data for a contour plot. And when I solve the table, and I'll use these results then to generate a 3D plot, so a surface plot, and the result is shown here. So I guess not surprisingly, as I move that strut mounting location towards the rear of the car or vertically down, either of those two things are going to cause the force that the hand has to apply to increase. And alternatively, I could move it up and to the right if I want to make the force from the hand decrease. But you get the idea that this is just a tool now for me to carry out kind of what if studies in terms of different design parameters.